This is about Trimble Business Center. These are some of the things that we'll be covering. We're looking at site calibration and local site settings in control, that's for control surveys, and also process feature codes, which is part of the merging of surveying and GIS. Also, we have CAD drafting tools, so anybody that's used TBC in the last 2 years will know that it's come a long way. It's a lot more advanced than it has been, and Trimble are quite serious about this product, and they've put a lot into it. So it still has the usual stuff that people would be familiar with, like network adjustment and processing baselines, but it's started to encompass all of this now. It's come at a good time because there's really some fairly significant changes in surveying currently. Surveyors have always used cutting-edge technology and the best engineering that they can find. Back in the day, they used theodolites and field notes to record what they were doing, and they're still using the best technology around, except now we have this precision instruments such as total stations and controllers, and instead of field books, we're using electronic controllers, and most of the work is being done in software packages such as Trimble Business Center. This slide shows the genesis of TBC. It's come from TGO and picked up a lot of the Terra model team along the way. So the developers that were responsible for developing those two products are now by and large working on Trimble Business Center. So it's got some of the best people in geodetics working on it. So we're sort of in a world now in positioning where people are used to getting ubiquitous, high quality, high accuracy positioning. So that's sort of come from a lot of the work that's been done on geoids, but also with the antenna calibration robots. We can now get down to around about the $2 coin size, which is about 20 millimeters. That's the kind of environment that we're in, but that creates its own problem. I guess it's no longer a theory of tectonic movement. It's more of we know exactly which way it's going and in what direction and on what speed. So the fact that the whole land mass is moving underneath us is sort of creating problems that in so much as, you know, like even casual users that are using WGS84 can now see the difference with a smartphone between GDA 94 and WGS 84. So I think in response to that, the government's come to the party and they're going to introduce a new projection, which will be GDA 2020, which kicks off next year. Now that's going to start out as a static projection, which from GDA 94 will be produced using a 7-parameter transformation plus a distortion grid, which will then, at 2020, become a dynamic datum, which means it'll be matching to ITRF, which means it'll no longer be X, Y, and Z, but it'll be X, Y, and Z plus time. So you'll need to know, for instance, if you opened up a file in 2025 that was created in 2020, your software might ask you, do you want to update to the current epoch? And it'll shift at the distance that the world has moved since that file was created. And that's underlined by some of the ICSM guidelines. Well, SP1, which everybody knows, is now quite upfront in recommending people do use GNSS for surveys. And this is also from SP1. We're sort of trying to work in this quick static, classic static area, possibly out to network RTK, but these are the kind of accuracies that we want to be working in. This graph shows survey uncertainty against observation time, and more or less shows that we're working with static surveys for datum quality control. And that's underlined by this table here, which is also from SP1. Notably, they've also shown that they'd like to see people combining terrestrial observations with GNSS baselines and producing new survey control marks from existing ones, and combining all of those using network adjustments. So this is a bit of an example showing how you might go about patching together a network adjustment. One of the things about network adjustment is that you're not supposed to use any closed figures, so it's all open figures. So if you were to propagate datum quality coordinates into this yellow area here, you'd first identify your horizontal marks and then identify the vertical marks, then tie those together with any potential baselines, make a plan of the ones that you want to use, and then work out how many sessions you would need to build up the profile without any closed figures. That is, without any trivial baselines. In this case, you'd need 4 sessions to make sure everything had been occupied at least twice. That way you've got redundancy in the survey. Then you take it back to the office, and in Trimble Business Center, you process baselines. Trimble Business Center has got an improved baseline processor now. It's certainly being used quite broadly with state government departments and amongst surveyors themselves. So it's one of the ones that probably is more reliable in the market. Also has the ability to perform network adjustments. I won't go into that at the moment because that could be a whole session by itself. Just to note that this is the preferred mechanism for adjusting surveys, and you can use terrestrial observations and GNSS baselines in this process to produce control coordinates. One of the things surveyors are encouraged to do is to connect to MGA or a datum. I know that the CSR in Queensland now requires cadastral surveys to connect to MGA if they're 10 lots or more. So some of these are the methods that you might use to do that. Like there's the old site calibration, which has been a bit of a staple for engineering and construction surveys for quite some time. It is still probably usable in a cadastral sense, so long as you recognise that if you use it, any errors that might be in the original survey will propagate into the site calibration. So use it with caution. If you take somebody else's site calibration, then I guess you're really working on their survey, not your own. But that would be to run a traverse around there, and that will produce an adjustment result, which is about adjustment. You then occupy some or all of those marks using GPS. Probably if you're striving for datum quality marks, then you would observe for 6 hours or longer, but a lot of people are using quick static, which is general purpose control, in which case you could occupy these for possibly an hour or two. So you build up the sessions and then process the baselines and adjust the GNSS part of the survey, and then marry the traverse and the GNSS adjustment together using a site calibration. That allows you to assess the fit between the two, and then if you're happy with the outcome of that process, you can save that site off as a local site, which you can load onto your controller. So anybody that's using that site is virtually choosing that on their controller as a projection for the job. So everybody's working on the same page and everything should fit together. Another example would be local site settings. Now this one takes the underlying characteristics of the grid, the MGA for example, and applies a combined scale factor to it so that the ground equals grid. Just to be a bit clearer on that, if you look at this situation here where you possibly would log a control network incorporating horizontal and vertical marks and densify as required, to do an inverse along that red line there that you can see, this TBC shows up because it tracks global, local and grid coordinates at all times. It shows the difference between the grid and ground distance for this vector at 146 millimeters over 370 meters. So that's the sort of error that you can't let stand in your work. So by applying the local site settings, that applies the combined scale factor to bring that difference to 0. Now that will work over a smallish area, maybe a couple of kilometers. You'll get away with that before it starts distorting again. So in a situation where your job site is 1 to 2 kilometers across, that is a pretty good solution, particularly if you're near to the middle of a UTM zone. As you're aware, this is a little bit of theory. If this diagram here shows half a UTM zone, you can see that the closer you are to the middle, the more square and perpendicular your grid is, whereas if you get further out, there's more angular distortion in it. But an example of how that local site settings works would be more or less fitting this green plane here to the surface where you are so that there's no distortion from that projected plane. So that works quite well where you're close to the middle, but if you're out on the edge, for instance, like that, and you've got that kind of problem with angular distortion, then you might be better off using a local transverse Mercator, which in effect takes the meridian that you're on and applies a UTM zone to that meridian with its origin at the point that you're at. So it will give you a good fit for your data, and ground will equal grid, but you must remember then that those bearings that you take on that system are no longer MGA bearings, and you'll have to translate it back to MGA before using them as MGA bearings. This is just an example showing integrated surveying. It's just to really highlight that you can also set up in MGA and work in MGA itself. This is usually more of an engineering and construction sort of a thing. It's because, it only works for very small areas, but it can be done. Like in this scenario, you've got an earthworks volume needed for tender for this. So what they want to do is get a topo survey done for this area here so that they can do a surface to surface volume from a design that they've got in mind for the site. So what you're really doing there, in this situation, they picked up the control at the same time as the topographic information. They used 2 points for logging static data and the third point as an RTK base, which they also used for logging as well, so by using an RTK plus logging survey style. and then half of the survey with the GPS or GNSS receiver, and half with a total station. So in this situation, you bring in the RTK and process that, and then scale in the total station data, working out what the scale is at that point, and then create strings and layer the data to then create a surface from that data. Now, from that surface, you can then create the design and then use that design to create a second surface and then do surface to surface volumes for tender. But before I move away from surfaces, I just wanted to point out that TBC's also got this suite of tools in it now where you can take the UAV data and create DEMs with that. So that more or less works by creating a point cloud from dense reconstruction. So it uses aerial photogrammetry to create it. And they've brought in RealWorks filters such as extract ground, which can be applied to, for instance, take all the trees out of that data so that you can then create a bare earth DEM to use for design purposes. I've also got a request in at the moment for them to add a D-spike function to those surfaces so that you can smooth it out even more. From a design perspective, there's tools in there for PDF takeoff, which is quite a handy thing. This is a tool that allows you to take a vector PDF and extract the line work from it. And once you've got the line work, you can then georeference it and elevate it. So that could be quite a useful thing. There was a situation that arose where a design was issued for construction drawings, which had DXFs with it for setting out, but the DXFs were different for the drawings. So they were able to, in that instance, take the vectors straight off the PDF and georeference them and use them in the field. For example, you can extract it straight off the top and use it for modeling and put that out as surfaces and line work out to a controller for set out for construction, or even out to machine control as well. The other thing that they've brought in recently has been this access to IFC construction models. Like that's the design standard for 3D modeling in Revit and Tekla, so you can bring these models through. In this case, you've got driven piles for a bridge construction. So these are quite detailed, these models. They get down to where the steel is and the lifting lugs for concrete panels, or even down to nuts and bolts. This is the driven piles in 3D. So anything that's in any of these models you can put on the controller and take for set out. So that includes the pads and columns and wing walls, as well as the decking and the surfaces and slabs for the bridge. There's also been a lot of work done in the as constructed area, particularly with respect to the XML transfer formats, such as ADAC. In this situation, you take the schema that's been specified by the engineers, in this case ADAC, which is more or less a Queensland and New South Wales standard at this point, but it's also being used in South Australia and possibly will be adopted more widely than that. In this example, it's under sewerage, you've got a non-pressure pipe, and under the attribute of use, you've got a whole lot of allowable enumerations. So what we've done there is we've extracted from that an FXL feature code library, in which we've included line control codes, as well as all of the attribute information for those categories. For instance, here under sewerage is also non-pressure pipe again, and under use we've got all the allowable enumerations. So that goes straight onto your controller. You can take that out into the field and pick up all of the attribute data that is required of you. And obviously these are formats that are eventually submitted to councils, and I think the idea behind that is that it'll get rid of the paper plan and even the PDF, and at the end of the day it'll only be the XML that goes to the council, and that'll be lodged automatically through a web portal service. So in this situation, you bring the data in that you've picked up in the field, and using all the line control commands you can auto draft that, so it's really just a 2-button click to get all the line work into it, which is a lot less painful than some of the old connect the dots systems that I've seen. And that's in perfectly in 3D, so we've tested that every which way we can, and we're certainly not losing any geometry in it. We've taken advantage of some of the advanced geometric features of Trimble Business Center and been able to work them into the ADAC format. You can see that all of the attribute information is held for each of the features, and it has spreadsheet functions and filters to help with entering attribute data. Then it's just a matter of actually selecting that data and exporting out to the ADAC format. And this slide shows the XML in FME, which is the software that most of the council are using to validate the data on the way into their data systems. As it ends up in GIS, we've also got tools that will write it directly to GIS. This ribbon here allows you to make a connection to an Esri database and to extract a schema or to write features to and from the database itself. So anything that's in GIS can be written out to TBC, and anything that's in TBC can be written into a GIS database. It's quite an open format and quite flexible, and we've tested that fairly extensively and it works quite well. This is just a little thing that I've tacked onto the end here. The object is to pick up this traffic island in, say, 12 points. So because that's a slip form curve and the slip form machines have a bubble on them that the operators are supposed to be aware of, it's assumed that this sort of curving is something where using offsets is quite a valid approach. So in this situation, you use Trimble Access, and measuring codes, you enter this code here. This RE3 is road edge, the third instance of road edge. The ST means the start, a line, and then there's two horizontal and vertical offsets. So by taking one shot there, you're actually picking up 3 positions. So you start there, move up there. This STTA is start tangential arc. On the other side, it's stop tangential arc. You move down to the pram ramp where you maintain offsets only, and then adjust the offset by allowing the back to roll out the distance of the ramp. Maintain that on the other side, and then readjust the offsets and run through 2 more tangential arcs before closing the string. So then you have 12 points back in TBC, which you can use this one-click auto drafting function, which is process feature codes, to give you that using those line control codes. And just to show that 3D, I made a little surface out of it so you could see that it works.